Today, I'm going through exercise 1.20 from the Art of Electronics. And in this exercise, we need to create a
full bridge rectifier
to the given specs. So this is the question, exercise 1.20. Design a
full bridge rectifier
circuit to deliver 10 volts DC with less than 0.1 volt peak-to-peak ripple into a load drawing up to 10 milliamps. So before we get started,
full bridge rectifier
it's basically a circuit that converts AC signal into DC signal. So what it does is it inverts the negative portions of an AC signal and turns them to positive. And then generally there is a capacitor after the inversion to smooth out any ripples. So this is the circuit that we will be using for designing this
full bridge rectifier.
So the two things that we need to calculate in this circuit is the size of the capacitor, which is given to us here, and then the input voltage that we require to achieve the 10 volts DC that is requested from the question. I will talk more about how the
full bridge rectifier
works in a simulation followed by this. And I will also upload a video going through the prototyping of a
full bridge rectifier
on breadboard. So let's get to the question. So as we know, this circuit is very simple, as in it only has a capacitor on the output to smooth out any ripples. So the maximum ripple current will most likely occur with the maximum load. So let's calculate what the load for this system is going to be. So using Ohm's law and the number of parameters that we know, so the output voltage is 10 volts DC, and we know the current is 10 milliamps. So then that gives us a load resistance of 10 volts divided by 10 milliamps. So it's 8,000 ohms. So a 1 kilo ohm resistor to represent our output or whatever we are connecting to our
full bridge rectifier.
The maximum ripple that we are allowed in this circuit is 0.2 volts. And that gives us a peak-to-peak voltage of 0.1 volts. As I'm in the UK, I'll be designing this
bridge rectifier
with a frequency of 50 hertz, but you can change this equation to 60 hertz or 120 hertz if you need to. So in the book, next to or near the question, we are given the equation of a voltage ripple or a change in voltage is equal to the load current divided by 2 times the frequency times the capacitance. Now, if we rearrange this equation to get to the capacitance, so basically 2 times the frequency times the voltage divided by the load current is equal to 1 over C. Now, if we invert the full equation, we get C is equal to I load, which is 10 milliamps, divided by 2 times frequency, which is 50 hertz, times by the voltage ripple, which is 0.2 volts. We get the following answer, which is 500 microfarads. The question itself is asking us to calculate the input voltage that would be required to get an output voltage of 10 volts. So let's note down some of the parameters that we know. So we know the voltage diode, which is given in the question, and it's 0.6 volts. So we know, or we can calculate the V in to be 10 plus 1.2, which is 2 diode voltage drops. So that gives us an input voltage of 11.2 volts, considering a voltage diode drop of 1.2. Now, in reality, this is not as straightforward. The diode voltage drop can vary with a number of different things. So it's not consistently 600 millivolts, and there is a significant effect from temperature as well. And I will show you this in simulation. The full solution to the question is given on the slide now. So we have an input voltage of 11.2 volts AC and a capacitor of 500 microfarads, and this will create an output voltage of roughly 10 volts DC with a load resistor of 1 kilo ohm. Let's create a simulation of this circuit to see how it works. So first of all, I'm going to start by placing the power supply. So I've pressed F2 on my keyboard to get place components, and I'm going to select a voltage source. Now to set the values and the parameters for the voltage source, you can click or right click on this, press the advanced buttons, and then go to a sine wave. So from our question, obviously we used 50 hertz frequency with an amplitude of 11.2 volts. I don't really care about any of the other parameters, so I'm going to leave them blank. Then we have a
Full bridge rectifier.
which is made up of diodes. So I'm going to place down 4 diodes to create our full bridge rectifier. And the shortcut for that is D. To place wires, you can press F3 on your board, or you can use this button here. So now I'm going to connect up the diodes to the power supply in the full bridge rectifier configuration. So I'm going to connect this point to ground and this point to our load. So we calculated a load resistor as 1 kilo ohm, and we had a capacitor with a value of 500 microfarads. So this is the full circuit built up. So let's see what it does. As we're doing 50 hertz, a 100 millisecond time frame for the simulation should be okay. So this is our input voltage. So you have a peak voltage of 1.2 volts and a frequency of 50 hertz. So that's our input signal going positive and negative. So we have an AC 50 hertz 11.2 volt signal going in. And now we can see the output voltage on this node here. So what I'm going to do is add some labels and call this V out. Call this V in positive and the other node V in negative, so that we have a better understanding of where we are reading the voltages. So again, we got our 11.2 volt signal and an output signal that is not correct. So what I've done here, obviously, is something very stupid. What I need to do is basically rotate these components into the H-bridge configuration because I neglected to do that. So to rotate components, you need to select the component and then press Ctrl R. So now you can see we are getting our roughly 10 volts. So I'm going to shrink the time frame again down to 100 milliseconds so we get a better idea of what we're seeing. So you can see now that we have a input voltage of 11.2 volts, and then we have an output voltage of between 9.5 and 9.6. So why is this different? Well, this is down to the diode voltage. So you can see the diode voltage drop on this is not equal to 0.6 volts. However, it is equal to approximately 780 millivolts. So instead of 600 millivolts, it's 784 millivolts. So we're going to have a bigger voltage drop. Now, if you think back to the equation, we use 0.6 volts. as our diode voltage, which was given to us by the question. But in reality, obviously, this is not the case. For a normal diode, it'll be something between 700, 800 millivolts. It depends, the diode voltage drop will depend on the temperature, as there's a relationship of approximately -2 millivolts per degree C. So that means the diode voltage will change in value by 2 millivolts per every degree C change in temperature. So let's say you have a -10 degrees of environmental temperature, then your diode voltage could be, let's say, 750 millivolts. And then as you go towards, let's say, 40 degrees C, then that diode voltage will drop and will be lower at the 40 degrees C, and the relationship is -2 millivolts per degree C. Now, to improve the situation, what we can do is maybe select some diodes that are more represented or closer to zero point 0.6, and we can potentially do that by using a Schottky diode. Now, I won't be able to control this diode voltage to get exactly 0.6 volts and to get to our solution, but this will be a lower voltage drop. So I'm going to try this Schottky diode, and Schottky diodes generally have a lower voltage drop across them compared to normal silicon diodes. Now you can see what's happened to the output voltage. We are basically having a ripple voltage that goes from 10.64 down to 10.469. Now if we do the calculations for this, so if I bring in a second marker, we can see the peak to peak voltage on this is roughly 200 millivolts, as we had calculated from our equation. So this all matches up to what we calculated, and obviously we got a slight difference in the output voltage, and this is due to the diode selection on the simulation. And this issue would affect you in real life if you're building this circuit. So you would ideally want to use some diodes that are very low in terms of their voltage drop, that will help to basically improve the efficiency of your circuit, as you will have less power drop. Now these diode voltage drops will change according to your load current as well, as they have a small intrinsic series resistors with them. So if you increase the current going through them, they will likely drop, or they will drop more of the voltage. So I will finish off with a question for you guys. How would you go about solving this variation in the output voltage to get the 10 volt DC output that is requested from the question? Let me know your thoughts below. That's all I have to share with you today, but I will be building this circuit using a breadboard, so watch out for that video. Thank you for watching. Bye for now.